Hello, welcome to Anselm Griffin's occasional series of YouTube tutorials concerning Matlab. Today we'll be looking at the end of the last lab and the lab we're about to do. That's week 2 for 022. So if you remember last week, most of you got the Excel done of the first order RUNGE KUTTA, and then we had to leave, so we had to do it in Matlab. So we have to solve that first order differential equation for the falling parachutist, and the formula was something like this. Now I can't remember exactly whether the drag coefficient was 4/15 or 3/15, but anyway, that's a constant. You can change that any way you want. So it's something like that. We want to solve that falling parachutist problem, and we're going to use RUNGE KUTTA 4/5 fourth order method, and then we'll have a look at it in the next slide. Okay, so that's just how it works. It takes 2 steps. Yeah, remember we were using step in Excel last week with h of something like 0.1, and then it uses 2 steps, and it compares the results, and then if they are different, the time step is reduced. But that's just nitty-gritty. Just to mention that these came from Jake Blanchard's website. So here's the code. You supply the time range, you supply the initial conditions. If you haven't used Matlab at all, this percent means it's sort of a comment. You call the ODE here. There's the function handler. The time range is 0 to 15, and there's the initial condition. So just slow down here. You get t and y. Y is the solution. ODE, that's the method we're using, which is 4/5, which is the most powerful of the numerical approximations. The function handler, the time range 0 to 15, and the initial velocity. You get the answer, and then we just did a plot, and I didn't bother doing the plot because I just speed up a little bit. There's my function, my mass, my g, and then the RK. Now note here, I've called the function f. It returns a value RK RUNGE KUTTA, and then it's minus g by minus 4/15 by y, by the abs of y over the mass. Something like that anyway. Okay, hopefully that's okay, and hopefully that makes sense. Now we're going to go on, so if you get that done, and then we're going to go to this week's problem, which I presume you've read. Maybe not. It's all about a pendulum, and just one thing, it is theta here, and I couldn't get theta to work, so I had to use phi, so that should be d theta. That's the general formula which you'll have read from your notes. Now if you remember, the linear velocity and the angular velocity is the same. Sorry, they're not the same. The linear velocity here and the linear velocity here are quite different. The angular velocity here and the angular velocity are the same here. So the linear is different and the angular is the same. So remember, d phi dt, that's the amplitude with respect to time, gives the angular velocity, and the second derivative gives the acceleration or deceleration, whichever way you want to look at it. So this is the second order because we're getting the second rate of change. The first rate of change, d phi dt, is the angular velocity, and the angular velocity dt gives me the acceleration or deceleration, whichever way you want to look at it, over time. First of all, you'll be asked to do it in Excel. You have to break it down into 2 first order differential equations. What's the first differential equation? That's the angular velocity d phi dt, so that's that one there, and then you do the second one, and that's the angular velocity dt, and the angular velocity dt is the same as d phi dt squared. Now I can't do any better than this. I mean, I know it's a little hard, but you just have to say, so this is the angular velocity, and angular velocity is d phi dt, and this is the angular velocity dt, which is the second first order differential equation. So we've broken it down into 2 first order differential equations. there's the formulas. I think they're right, guys. I may have made a mistake, but I think I typed it up right, but you just never know. I may have got something wrong. I left out the weights at the end there in the notes, and there I did a bit of a screen dump from Excel, and I've given you, say, some of the, you can just about K1, L1, K2, L2, so there's other stuff out there. And remember, further out here, as you see in your notes, you have to get the weights. So, but just to give you a start, once you get that done, you have to do it for Matlab, and same crack as before. You have a function x dot, so it returns x dot. There's x dot there. The name of the equation, pendulum. Two inputs t and x. There's some constants there I just made up. You can change them as you go along. So this one is the first derivative. That's the angular velocity, d phi dt. This one represents the angular velocity dt, or d2 phi dt squared. Well, we can't say d2 phi dt squared. We've got to say the angular velocity dt. So x dot will return that. So there we are. There's the time span 0 to 20. There's my initial conditions. There's my answer. I call it pendulum equation. The time span as before, comma 0. Now, I want you to do some plots for me. X will return. There'll be two columns, so I want you to tell me what the first column is, what the second column is, and I want you to plot them on the same graph. Okay, so hope that helps a little. Thanks very much for listening.